It seems students do not understand the non-mechanical deformation clearly. That's why I'd like to prepare these slides to explain the concept of non-mechanical strain. The very first step to discuss that issue is to recall my map. So according to my map, we have force here, and then the stress, the force becomes stress, and then we have strain. And then we have the displacement. This is the map of analysis that I emphasize every time do my lecture. So from the displacement, we can obtain the comparable strain, and then from the material law, we obtain the stress, corresponding stress, and the integrating stress, it becomes internal forces, and the internal forces should satisfy the force equilibrium. And then also the direction of flow can be started from the force side, and then it produces stress, and then we calculate corresponding strain, and then displacement. And then we said that this path is called compatibility. And this is called material law. And then this part is called equilibrium. Okay, look at this. Here today we'd like to talk about a little more about the strain part here. Actually here we can calculate strain from two different directions. So once we have certain stress value, then we can calculate the strain. By means of what? By means of the material law. So in this class, we are using the Hooke's law. So what I mean, if the strain is caused by stress, it is linearly proportional to the applied stress. That's why the strain caused by stress is given by stress divided by elastic modulus. And then the second path is what? From the displacement. If we have a displacement field, we have strain here. And this is comparable strain. So if you consider the superposition of strain, say the total strain total strain is the sum of strain caused by stress and also strain caused by the other effect, that becomes the total strain. So make sure that the total strain, this is the strain, apparent strain. This apparent strain must be subjected to the compatibility. And this is compatible strain. This is compatible strain, okay? This is compatible strain. And then the first term in the right-hand side is mechanical strain. The strain caused by the mechanical stress. And then the second term in the right hand side is non-mechanical strain caused by the temperature change and humidity. And that's what I explained here. The total strain can be decomposed to the mechanical strain and the non-mechanical strain. And then also we can do the same thing for the strain rate too. In the modern form of finite element analysis, especially in dynamics, and then the nonlinear finite element method, we use the strain rate decomposition to the analysis. Okay, one of the best example regarding the non-mechanical strain is the thermal dilatation. In the case of thermal dilatation, there is no stress. We do not have stress. If you increase the temperature of the bar, then the length of the bar is elongated by delta t. And then if you divide delta t by the original length, and we call that the thermal strain. Okay, So let's consider example here. I already explained some of examples in the classroom, so I'd like to discuss a little bit more about the issue of non-mechanical strain using pre-stressed column. Actually, in modern reinforced concrete designs, we use the pre-stressed concepts in many different places because the concrete is weak in tension but stronger in compression. That's why to take advantage of that, the stronger compressive behavior, we introduce so-called pre-stress. The concept is here. So we have concrete column, but in the middle of concrete column, we embed pre-stressed tendon, so that if you release the force, the pre-stressed tendon produce compressive stress to the concrete section. That's why the initial stage before the loading is already compressive in the concrete side. That's why we shift the stress condition to the compressive side from the first, and that then we can take advantage of the stronger or wider domain of compressive side in this pre-stressed concrete column. Okay, to explain the problem in detail, I'd like to consider two different extremes. In the first case, the reference length, there is no mistake in the length of the concrete section. And then, but the tendon, the preset tendon is a little bit shorter than the reference length by delta. That's why what we have to do is we have to stretch the tendon to the height of the concrete, and then we fix them together and we release the loading. Then because of interaction, and then the overall column is shrink down. Okay, and then in the case of second case, there's no length error in pre-stressing tendon, but the length of concrete section is a little bit longer than the reference length by delta. So in that case, what you have to do is we have to compress down the concrete section to the pre-stressing tendon point. So let's consider these two different cases for a comparison. Okay. So here, the very first step is what? The very first step before any analysis, we have to introduce coordinate system. So my coordinate system is here. Because the bottom is fixed, so I want to introduce this coordinate system. So here, the one-dimensional problem, and then this is equal to 0 here. The origin is placed on the bottom of the column, and then this is x-axis. This is my coordinate system. Okay, because this is a prismatic section, and then the deformation is homogeneous. That's why the displacement change as we release the action, then it should be linear. And then at point A, there is no displacement. Displacement should be equal to 0 because point A is supported. And the point B is a free end. There must be the end displacement, the UB. And then if you draw a straight line connecting point A and point B, and that is the displacement field. And make sure that we are talking about the prismatic section. The deformation is homogeneous. The slope is the strain. Okay, because this is prismatic problem, my strain is constant over the entire length of the column. And then make sure that this strain is subjected to the compatibility, displacement compatibility. This is compatible strain because it comes from the displacement field. Okay, so to define this compatible strain, we never talked about force, and we never talked about the action of misfit, not at all. Okay, we just considered a certain form of displacement and the corresponding strain. That's why we call it compatible strain. Okay, what's the next step? So we just calculate the compatible strain. The next step is we need to trigger the material law. So let's talk about stress-strain relation. So now we have two different materials. The first one is concrete, and the second one is steel. In the case of concrete, So we have, we do not consider any non-mechanical strain. That's why I'm talking about the first problem. Because of first problems, we introduce misfit only to the tendon. That's why when you talk about concrete, the strain of the concrete is totally caused by stress in concrete. That's why to calculate the strain, the comparable strain is surely due to the mechanical strain. That's why stress in concrete is sigma c divided by the elastic modulus of concrete. And then this is the comparability condition, isn't it right? And then in the case of steel, so because we introduce non-mechanical strain, the non-mechanical strain is what? The tendon is a delta shorter than the reference length by delta. Because it's shorter than the reference length, that's why the sign should be minus, okay? It's a negative strain. So if there is any stress in steel part, and then this stress causes also the strain. That's why the strain in tendon is strain due to the stress and then non-mechanical strain. The sum of these two strain contributions, that becomes a total comparable strain. So again, make sure that the comparable strain is same as before. The same comparable strain and same comparable strain. Okay, so let's plug in the strain to the equilibrium condition. So now let's talk about the equilibrium near node B. Okay, here there is node B. In the case of node B, here, oh, by the way, I didn't mention node A and node B. But node A is bottom, node B is top. So in near node B, there is no external load. That's why if you consider the free body diagram in the cross section, we must have the stress in the tendon and then stress in concrete. Isn't it right? Sorry. Stress in the concrete section. Isn't it right? So because stress is not a force yet, we have to integrate the stress to make forces before we check the force equilibrium. Okay, so because there is no external force, okay, and then the integration of stress of concrete and the integration of stress of steel over their cross section should be equal to 0. So let's plug the information of strain here, strain into here, and also the comparable strain into here. Then we can rearrange everything with respect to stress value here and also here. So let's plug stress into the equilibrium equation here and also here. Then finally, we can obtain the expression of stress in terms of the nodal displacement of node B. So we can calculate the nodal displacement. This is the final answer. So the nodal displacement of point B is what? It's minus, it is proportional to this coefficient and then delta. That means the column is a little bit shrink down. The length of the column is reduced from the reference length L. Let's consider the second case. In the case of second case, we introduce the non-mechanical strain to the concrete part rather than the prestressing tendon. For example, look at here. So we have the concrete is a little bit longer than the reference length by delta. That's why here, to calculate the strain, the comparable strain of concrete is sum of mechanical strain of concrete and then non-mechanical strain of concrete. Because now the concrete is lower than the reference length. That's why the non-mechanical strain, the sign of non-mechanical strain is positive. In the case of steel tendon, in this case, there is no misfit and non-mechanical strain for the steel. We do not consider that. That's why the comparable strain is totally equal to the mechanical strain of steel. Okay, by the same logic, so I want to check the force equilibrium near node B. And then we plug the information of stress into this force equilibrium equation. Then finally, we can solve out for the nodal displacement. Here, the nodal displacement is what? It is also proportional to this coefficient and then delta here. But the sign is positive, which means if you release the action which press down the concrete section, after the concrete section behave a concrete section and the steel tendon behave as one piece, then the overall length of the column is a little bit increased compared to the reference length. That's why it has positive sign. Okay, so let's compare these two displacements together. Let's divide the nodal displacement of case 1 by nodal displacement of case B. So in that case, because we can cancel out all the common term, so we have this relation. Here, the first term in the right-hand side, ES divided by EC, is called, this is modular ratio, the relative ratio of the material modulus, elastic modulus of steel and to concrete. It is roughly 10 to 20. And then the second term is the reinforcement ratio, or the area of reinforcement steel to area of concrete section. It's typically 0.1% to 0.2%. Then if you plug this number to the first equation, then we can obtain the relative dimensionless displacement is about minus 0.1 and to 0.04. What I mean is from 1 to 4%. So what I mean, the displacement of case 1 is much smaller. The magnitude of displacement case 1 is much smaller than case 2, but the sign is different. That's what that means. If you introduce pre-stressing tendons, pre-stressing to the column, so we'd like to introduce non-mechanical strain to pre-stressing tendon, because the length change is smaller than the second case. Okay, that's all. So if you have any question, and please let me know.